Hi guys, today we're going to talk about solving systems of linear equations. It doesn't specify that, but systems of linear equations, both graphically and algebraically. I went ahead and split it up into two separate sections. So for right now, we're going to talk about solving a system of linear equations graphically, just to try to shorten up each video and make them a little more manageable. So to solve a system of linear equations that contains two variables, two equations with two variables, write each equation in slope-intercept form, graph each line on the same coordinate plane, same Cartesian plane, determine where the lines intersect or if they intersect, and the point of intersection is called the solution. So let's start by solving this system by graphing. Notice that the first line, and I'm going to label these just to make it a little bit easier. It might be useful to label each line as you're working to go through. So the first line is already in slope-intercept form. Notice that the slope, remember that we identify that as the variable m is 1/3, and the y-intercept is -2. I'm going to write that as an ordered pair. A lot of times students forget that that's a point on the line. Okay, so let's go ahead and just take it easy and let's graph that line. So we have a y-intercept of -2 on the y-axis, and we're going to rise 1. The slope is a positive value, so the line should be increasing from left to right. So we're going to go up 1 and over 1, 2, 3, plot a point, and we can do it again. Up 1, 1, 2, 3, plot a point. And if you want to go in the other direction, down 1, 1, 2, 3, and back. There we go. Plot a point. And then let's go ahead and draw that line. Let's give it double-headed arrows, and we're going to make this one green. See if we can get this accurate. It's going to be careful. There we go. Okay. Let's take a look at the next one. In this case, we actually need to put it in slope-intercept form. Notice that for this one, it's currently in standard form. We need to get it to look like y equals mx plus b to graph. Of course, it's not absolutely necessary. You could use intercepts, but we're just going to go ahead and put it in slope-intercept form. So the first thing we're going to do is we're going to subtract 3x from both sides, from each side of the equation. We're going to get 3y equals -3x plus 6. Divide every single term by 3 to isolate y. We're going to get y equals -x plus 2, which tells you that your slope is -1, and the y-intercept is the 0.02. So now we're going to graph that line. So we're going to go to 2, +2 on the y-axis. The slope is -1, so remember that that means the line should be decreasing from left to right. So we can go down 1, but to the right 1, and do it again. Down 1, right 1, down 1, right 1. Notice that point is something they have in common. It's a good idea when your points are so close together to plot multiple points there, and it's not a big deal to put a bunch there. And it's the closer the points are, the more mistakes we could make with accuracy in graphing. So it's a good idea to plot multiple points and then line them all up on the same straight edge to identify that point of intersection a little bit. Let's see if we can straighten that out a little bit. There we go. Okay, what we're looking for is whether or not these lines intersect, and if they intersect, what is that point of intersection? That would be the solution to the equation. So notice that these two lines intersect at this point right here with coordinates 1, 2, 3 to the right and down 1. So that's the ordered pair, +3, -1. When you write the solution to a system of linear equations, you always need to make sure that you put it in ordered pair form. Otherwise, you're just talking about, we don't know whether you're talking about the solution to a system. If you're doing that, maybe you're just identifying the solution to one particular equation. So make sure you always write that in parentheses, the solution to an ordered pair. Sometimes we have different types of systems, just so you know. So let's talk about those different types of system. An independent system is a system with exactly one unique solution, just like what we graphed on the previous page. If the two lines intersect at exactly one point, then we say that it has one unique solution, and we call that system independent. Okay, and you do need to be able to identify a system of equations as either independent or dependent or inconsistent. We're going to talk about these as well. So a dependent system has infinitely many solutions, and a dependent system is one in which the two lines actually are identical, so they appear different maybe when they're in standard form, maybe one's in standard form, maybe one's in slope-intercept form. They might have the appearance of looking different, but when you eventually put them both in slope-intercept form, they actually are identical. They have the same slope, and they also have the same y-intercept. So they are, in fact, the exact same line, okay? And in the case of an independent system, they have to have different slopes. That's kind of a requirement. So we're going to mention all this again one more time. And an inconsistent system, in an inconsistent system, there's absolutely no solution. You'd be looking at two parallel lines, and there's no point of intersection. There are no points that they have in common. This means they have the same slope and a different y-intercept. And so we're going to talk about that on the next page briefly, so you can determine if a system of equations is independent, dependent, or inconsistent, specifically by looking at those things. So an independent system must have different slopes. If two lines have different slopes, somewhere or another, they are going to intersect. A dependent system has same slope and the same y-intercept. And an inconsistent system has the same slope. Remember that parallel lines have the same slope, but must have different y-intercepts. Okay, so let's talk about classifying a couple of systems just like that, thinking about what we've got and how we can do that algebraically without actually graphing. So in the first problem, we've got y equals 3x plus 2 and negative 6x plus 2y equals 4. The first one's already in slope-intercept form. Let's figure out slope-intercept form for the other line. And we get 2y equals 6x plus 4. Divide every term by 2. And we end up getting y equals 3x plus 2. Notice that this is identical, right? This line is now identical. Same slope and the same y-intercept. That means they must be dependent. It's the exact same line. Nice if I could spell dependent. A dependent system. If you're trying to write the solution to a dependent system, and you're not necessarily always asked to do that, but if you are trying to identify the solution to a dependent system, in Algebra 1, frequently we'll just say there are infinitely many solutions. That happens a lot because we're talking about all the points that lie on the line. So in Algebra 1, we'll say there are infinitely many solutions. But also in set builder notation, we would say the set of all ordered pairs xy such that, so we use a colon to represent such that, they satisfy the equation of the line, and I started to write the 3x plus 4, such that y equals 3x plus 2. And what that really means is we're talking about every ordered pair that lies on the line given by y equals 3x plus 2. So there's a couple of different ways to identify that solution. In Algebra 1, it is very common to just say infinitely many solutions. Or you could just talk about the fact that it's the set of all ordered pairs that lie on the line given by that particular equation. All right, let's talk about this other problem right here. 3x plus y equals 5 and 15x plus 5y equals 2. We're going to start with this first equation, a, b. So I'm going to take a look at putting a, which is 3x plus y equals 5, into slope-intercept form. So I'm going to subtract 3x, subtract 3x. We're going to get y equals negative 3x plus 5. And we're finished with that one. Now let's take a look at this other one here. For this equation b, we have 15x plus 5y equals 2. If we subtract 15x from both sides, then we end up with 5y equals negative 15x plus 2. Divide every single term by 5, and we get y equals negative 3x plus 2/5. So here's what I notice about this particular system. Notice that the slope will be the coefficient in front of x when your equation is in slope-intercept form. So the slope is negative 3. Also here, the slope is negative 3. But notice they have a different y-intercept, right? So same slope and different y-intercept means the system must be a system of two parallel lines, which means it is an inconsistent system, right? If you were going to identify the solution would be no solution because there are no points in common, okay? And then what you should do is I'd probably pause right here and work some of those questions involving graphing systems or solving a system of equations by graphing and classifying systems as independent, inconsistent, or dependent. And then I would pick up and go through the notes on solving systems algebraically, which is what we're going to pick up next. Okay?